talking Amir Lodge. Amir is a faculty at Weizmann, and he's currently visiting NYU. Amir has worked on many things, including fine-grained complexity detections between different problems and graph problems, and so on. And today Amir will be talking about min cuts and also transform.
Thanks for watching. Thanks everyone for coming, for the invitation. Very nice to be here. So today I'm gonna ask and discuss the relationship between two very fundamental, very basic graph problems, graph parameters, the shortest path and the minimum cut, and I'm gonna try to discuss which of them is easier than the other. So here are the two problems. So what I want to discuss is the relationship between shortest paths and maximum flows or min cuts. So as you all know, minimum cut and max flow are equal. So in any graph. Okay, so in both problems that we're discussing, we have a graph and we have a pair source and target S and T. And each of these problems asks different things. The shortest path asks for the cheapest way to go from S to T. So you try to find the path and you want the total weight of the path to be as small as possible. And minimum cut or max flow, it's different. So in max flow, I guess you're asking for the maximum amount of flow you can push from S to T while respecting the edge capacities. And the answer to that is equal to the minimum cut between S and T, which is the minimum amount of edges you need to delete from the graph to disconnect S. So in this example of this graph, if these were your S and T, this blue cut here has a cost of 11. The total weight is 11. And it's a minimum ST cut. There's no better cut in this graph. Like there's no cheaper cut either. And it shows that the maximum flow is equal to 11 as well. So throughout the talk, I'll use min cut, max flow interchangeably. We will really, for all purposes of this talk, they will be the same. So you can think about whichever is more convenient for you. And good. So these are the two problems. You've probably seen them a long time ago, and maybe you like one more than the other. Maybe you have an opinion of which one is easier or harder. So let's talk about that. So how do you compute these things algorithmically? So for shortest path, there's Dijkstra's algorithm. It's a classical, very simple algorithm that runs in this time. So graphs, we're going to have n nodes and m edges. So the running time is like near linear, n plus n log n, and it computes the shortest path. Great, so that's like super fast for us, like almost linear. Let's say the situation is more complicated for max flow. Around those years there wasn't even a polynomial time algorithm. Running time depended on the value itself. And then throughout the years, the better, faster algorithms were developed. Some combinatorial algorithms getting m times a function of m. And then in the last decade or two, there was this method using continuous optimization, Laplace system solvers, all sorts of things. And they've been making breakthroughs on the running time of max flow. And since these works, like when I would go to conferences around those years and I would talk to the experts, they would tell me, yeah, with these things, they're so powerful, they're going to get at almost linear time. At some point, we just need, it's just very hard to do it. But the point is, like, experts believed it was leading to linear time. And, in amazing breakthroughs in the last couple of years, this was indeed accomplished. So this paper gets almost linear time. So number of edges to 1 plus little over 4. Okay, so for me, let's ignore these subpolynomial factors. Let's just ask in terms of like the exponent. And the conclusion is that both of these problems turn out to be easy problems, like linear time solvable problems. Of course, shortest path was much simpler. This is a super simple algorithm. Plan it and analyze it like half a page, whereas this is super hundreds of pages of work, and it's very, very complex. Okay, so shortest path is simpler, feels nicer, but There's no like separation between them in terms of complexity. Okay, so let's try to find some other ways in which they are different. So from now on, I'm going to drop m. So I'm just going to think about like dense graph, like worst case, where m is up to n squared. And so the running time for the problem is n squared, and this m is that. One thing to observe is that when you run Dijkstra, you don't only solve the ST problem. You don't only find the shortest path for a single pair. You actually get this shortest path tree from the source to everybody. So you run Dijkstra once, and you get this single source information. You find out the distance from S to everybody in the same time. So it's still n squared. The same is absolutely not true here. When you run these algorithms, you only get the answer for one target. If you want to know for more targets, you have to run it again and again. So then this gives this complexity n times whatever running time you had for the single pair. That's what you can do to solve the single source problem. Okay, so here we're starting to see a gap. So maybe that's gonna give us the separation. And so let's look at the more general problem in this context where they all pair. So you just use one graph, and you want to know for every pair what is the distance or what is the minimum cut. Okay. So what is the complexity of this problem? And let's just simplify. We just want the values. We don't care about the float themselves or the paths themselves. We just want to know the answers. So the output side is n squared. The output side is n squared numbers that tell you all the distances or all the flows. What is the complexity? Here, of course, we can just run the single source algorithm from every source. So n times running Dijkstra n times runs from every source gives us the n cube. Of course, there's these other Freud, Warshall, all these other algorithms there. We're ignoring log factors, it doesn't matter. So it's just, for us, it's n cubed, and this was known, since Dijkstra's algorithm, essentially. So it's super simple, long time ago. Here, so you can still run the naive thing. So for every pair, you run the ST algorithm. And that gives you, with what we know now about the single pair, which is quadratic time, you get n to the 4. Okay, so this is, again, like a naive kind of sound. But actually, in 1961, a long time ago, there was a breakthrough, a very nice paper that I'll discuss in a bit, by Gomory and Hu, where they showed that this all pair problem can be solved in n times single pair, not n squared. So you only need to run single pair algorithm n times. So let me tell you about this result. So it's they proved this theorem, which is a fundamental theorem about graphs. It says that any graph has a cut equivalent tree. So what this means is it's a kind of like a graph simplification. It's like a super powerful graph sparsification result. So you can take any graph, even if it's weighted, and you can turn it into a tree. So this tree is on the same set of vertices, but it's a tree, it's much simpler. And it's cut equivalent. So the tree has some weights that could be different. But the point is that now once you have the tree, you can look at any pair, SMT, any pair that you want. You can, if you want to know their minimum cut in the graph, you can just find the minimum cut in the tree, and that would be the answer. So, for example, if this is the pair you care about, SMT, just find the minimum cut on the tree. So that's easy. You just find the cheapest edge on the path between them on the tree. In this case, it's the 11. So this cut is it's a bipartition of the vertices. It's a cut. So take that same cut in the original graph. So same kind of bipartition. What you get is a cut that has the same value, this 11, and it's also promised to be a minimum cut. So it basically showed that the problem that we care about, this all pairs max flow problem, in any graph is reducible to trees. And not only did they show that this is like existential, they even showed that like their proof was algorithmic, and it gives an algorithm for, like their proof is an algorithm essentially for computing this tree given any graph using n minus 1 calls to a minimum cut algorithm, single pair minimum cut algorithm. Okay. And once we have the tree, like solving our problem over much flow, it becomes very easy. You just for every pair, you just need to find the cut in a tree, which you can do in like log n time. So really the question is, how do we get the trees? And they gave this n times max flow algorithm. If we could get the tree faster, we would have a faster algorithm for all pairs match. And this has been open pretty much since their work. Can we get anything faster for computing the tree? Any little law of n times max law, and nothing really happened for a long, long time. Meanwhile, we go back to the all-pair short path, which also had this kind of cubic bound. There were many, many papers shaving some factors over the n cube, some log and polylog and super polylog factors. So the exponent is still n cubed. So if you ignore all these things, it's still at n cubed, but like it felt like something was happening, and maybe there is something one can do here. Whereas for max flow, it was completely stuck. Okay, so back to the comparison of the two problems. So what I've said so far is we're looking at these all pairs problems, shortest path max flow, we're trying to compare them, which is easier, which is harder, and that's the summary. Both are at n cubed. And we certainly felt that max flow should be hard. Like if one of them is harder, it's got to be the max flow. Why? Well, because the single pair was so much harder to solve. It's just a complicated problem. This thing that I just mentioned, in APSP, we have these a bit subcubic things. There we don't have. Let me mention two more reasons to think that shortest path is easier. So one is if you look at unweighted graphs, where you don't know the weights are one in the graph, super fundamental natural setting. There you can actually break the cubic barrier for shortest path. So there are these old algorithms using fat matrix multiplication, basically reducing shortest path to fat matrix multiplication, and getting into the omega time. So that's subcubic, whereas in the same setting in unweighted graphs, we didn't know any subcubic algorithm for max flow. Okay, so in this natural setting, there is a separation, and I'm showing that shortest path is easier. And here's another fundamental setting, directed graphs. So if you move on to directed graphs, shortest path, everything still works, the still works. You're still at n cubed. Whereas if you go to max flow, the Gomory Hu result completely breaks. So this fundamental object, these trees, it just doesn't exist for directed graphs. Directed paths are just weird. So they don't behave the same as undirected. So the complexity was still at 10 to the 4. So here's another natural setting where there's a separation. Again, in the same direction. Max flow is harder. Again, here's a summary table. So we got into this thinking about this, and I think everybody was thinking max flow is at least as hard. Let's just try to prove this, formalize this. And that's exactly what we like to do in fine-grained complexity. We try to show connections between problems. So fine-grained complexity is this literature of where we take, fundamental natural basic problems, more than one. We try to, understand what is the complexity, what is the relationship between them. So you can look at before, right, we had all these nice problems. We didn't really know what's going on. All these problems are some polynomial time solvable problems that people want to solve. And, APSP, APMF are just two out of them. And, we've been designing all these cool reductions that let us show some more understanding of what's going on by pointing at some core problems, some conjecture to be hard problems that, a lot of people have thought about for many, many decades, and have good reasons to think they're not solvable any faster. And then using those conjectures, we can classify, dozens and dozens of other problems. So showing that for any problem here in this class, and there's dozens of them, whatever bound you have now cannot be improved by a polynomial factor. The exponent cannot be improved unless you break the conjecture on top. So this is like fine-grained complexity. And so this asking us to show this connection between all pairs max flow and the APSP is a very natural question in this field, because in particular, APSP is one of the conjectures. So one of the three main conjectures in the field hypothesizes that n cubed is the limit for APSP. So you cannot get into the 2.99. And it's a conjecture that has led, a lot of graph problems were shown to be at least as hard as APSP, in the sense that they cannot be solved in subcubic time unless APSP can. So, all we have to do is put APMF in this class. So that's kind of the question we were investigating. And so, yeah, I've thought about this since I was a first year PhD student, and we did come up with some proofs. And so in particular, we did show that APMF is harder, but actually only in directed graphs. And if you remember from a few slides ago, directed graphs are not that interesting because the Gomory and Hu result doesn't apply there. So in this setting of directed graphs, we showed some hardest results that I don't really want to go into, but basically they're saying, this bound, maybe it can be improved a little bit, but you can go below n cubed for sure under set or famous conjectures, and there's other variants of conjectures where you can't even get to n cubed. But anyway, so good. So that showed, proved our belief that max flow is indeed harder, but we were not really satisfied with this because directed cuts are weird. It's not, it's not revealing the answer to the question we actually cared about. Okay, so we drop that and we just go back to undirected graphs, and there we didn't have anything. We didn't have any lower bound for the problem. Okay, and now I want to give credit to fine-grained complexity here, because when I started thinking about these things, I would look at all these cool problems that I hear about, and I may be working on algorithmic problems where super nice problems people are stuck on for decades. And I could find myself working on any of them and thinking about any of them, and I wouldn't find it reasonable to spend like 5 years working on one of these problems, because why not work on all these other ones, and so on. What makes you choose this one problem? They're all so nice and so on. But actually, when I look back at this, a few years later, the picture by that time was very different. It looked kind of like this. So we have the red problems, which were highlighted as conjectures. You have to be very brave, very ambitious to work on them, and maybe I wasn't that brave. But then all the other problems, they were grayed out. So there were reductions from the red problems to them, showing that these problems you can't solve them until you solve the red problems. So don't work on them. You can if you want to work on them, work on the red problems first. If you're brave. Okay, but then the all pairs max flow stood out among kind of my list. It stood out as a super fundamental problem that has resisted improvement for decades, yet there's no kind of reason for it. So we did work on this problem for a few years. I had a summer intern working with me, Ohad Travelsi, who was a PhD student with Robi. And we started proving some results here and there, beating around the bush. I don't want to go into them here, but we were convinced that it's a hard problem. We were just trying to explain why we can't show lower bound, non-reducibility result, and all sorts of other things. But then suddenly we started thinking, hang on, maybe it's not really a hard problem. And we did come up with this paper, which we were very proud of, where we broke the cubic barrier for all pairs max flow in unweighted graphs. This was the first improvement over Gomory and Hu. So the running time was n to the 2.5. And then things started accelerating. So after 6 months, there were 3 papers improving this all the way down to n squared. So what this meant is that the table now looks like this. Everything is for unweighted graphs. What was n cubed is now n squared, which is super cool because it's optimal. Like the output size n squared, and you can just and even the input size. So you can't do anything better than that. And so we kind of solved all pairs max flow like optimally super fast. Turned out to be kind of surprisingly easy of a problem. And for the first time in history, we have like max flow becoming easier than shortest paths, which was like a very disorienting situation. But then we said, okay, maybe it's not so strange. So, just like the experts on max flow were saying it's going to be linear, the experts on matrix multiplication are saying it will be quadratic. Omega will be 2, so wait 100 years, and then both of these things will be n squared. And it's not surprising. Sure, both problems are easy, undirected, unweighted graphs are simple and good. So then, yeah, we really kept working on this, and we got to solve the weighted case faster. So we joined forces with the other people working on this, Jason Lee, Malik Ibrahim, Sajjad Sar on the rock. And we solved the problem even in weighted graphs in quadratic time as well. So now this is like a separation, at least if you believe the APSP conjecture. So here there's this conjecture that the experts are putting, in the sense that it's not like the experts think it's gonna be quadratic. No, the experts think we don't have any strong reason to think it will be subcubic. Whereas for max flow, it's quadratic, so it's like much faster. So if you assume the APSP conjecture, or even a mild form of it, like okay, maybe it's not n-cubed, maybe it's 2.9 or so. Even then, you get this separation, which is in the opposite direction of what we expected. Max flow is easier than shortest paths. So yeah, so the kind of if one still can't stomach the idea that max flow is so much easier than shortest paths, then the only conclusion is to say, well, then the APSP conjecture is just false. It can't be true. So maybe that's the case, and I'll spend like the second half of the talk discussing what we might learn from this result to try to attack the APSP conjecture. So I'll discuss that later. But yeah, before I get to that, let's maybe talk a little bit more about APMF, just conclude the story. So in the paper, when we solved it in n squared, we asked 3 questions. So let me ask them here and report some progress. So I said n squared is optimal, and right? It's optimal only if you have a length graph, and we like sparse graphs usually. And it's also optimal if you need to output all the answers, the n squared answers. But actually, you're maybe just satisfied with the tree, just computing the Gomory and Hu tree, because once you have it, you can just, if you want to know the answer for some pair, you can just look it up in the tree. So like it would be much more satisfying to get m time, not n squared m, to get the tree, and this was accomplished a year later. So this result, like showing that in linear time, which is also the max flow time, like single pair max flow, just in that time up to polylog factors, you can get the whole Gomory Hu tree, and then you know the answer for all pairs. So the message is that all pairs is really not harder than single pair or max flow. So that's basically the algorithmic message of these works, which a priori it's not totally not obvious why finding one minimum cut teaches you everything, but that's basically what happens.
Is this black box on the other max flow results?
Yeah, everything we've done is kind of black box. You could have plugged in any algorithm for max flow. To actually go from n squared to m, we did use machinery that looks similar to what they're doing. So we did use dynamic data structures and so on. Simpler and different, but let's say there's some common machinery, but at the end of the day, it's a black box. And if you want just the n squared, it's very, very, I would say, simple. So that was the first question, and the second question was getting things deterministic. We're using randomness everywhere, and this was also solved by now. So you can do everything deterministically, both the max flow component and the hour reduction. Everything is deterministic. And one thing is we would really like these things to become simple. Like we'd like to see a simple reduction from all pairs to single pair. From our work, it was very far. It has become much closer. So there are these papers by a group from ETH, a couple of papers, one even in SOSA, where they're simplifying things a lot. They're kind of saying, all you need is some expander decomposition and a couple of other things, which I'll mention in a bit. It's still not simple enough for me to present in like half an hour, but it's getting there. Okay, so that's kind of the end of the story, and what I want to do next is we'll try to give you 5-10 minute overview of the max flow result, and somehow kind of set the stage for some of the next part of the talk where I will try to explain how these ideas might work for shortest paths. Right. And the shortest paths part, it will be mostly like fantasy, wishful, but I'll report some actual results that we accomplished, so it's not just fantasies. Okay, so I want to describe the algorithm, but I want to start with this framework, high-level framework that is common to a lot of algorithms, especially modern ones, where you can kind of break it up into 3 components, and I'll say what these components are when we talk about max flow, and then I'll say what they might be when we talk about shortest path. So algorithms typically involve some kind of heavy tool that you kind of use, and for us it will be like the single pair max flow. That's at the end of the day, all the heavy lifting is kind of there, so it's a heavy tool that you use. In other places, it might be a different. On top of this tool, you do some other things. So maybe you do like this. So in this tool, it might be using all sorts of things, some algebraic things and whatever. Okay, but on top of this tool, you need to do some kind of algorithmics, some divide and conquer, sampling, or so it's kind of elementary or some combinatorial stuff. So that's kind of also there. And it can be very rich, very interesting, very complicated But then there's this third component, which is very popular these days and very powerful for all sorts of problems, which is where you take like your input and you try to like find some pieces of it that are more like this, more like that. Some pieces are more like random, some pieces are more like structured in some way, some pieces are sparse. So this is what I'm like calling structural analysis of the graph, the input, which has been used under different names, like data dependent. You don't do something that's for every input. You just look at your input and try to find pieces of it. Another way to say it is worst case to average case, where you say, I know how to solve it on random, and then I just take my graph and I find these random like pieces and I solve them, and the rest has to be easy for some other reason. And in our applications, we have used expander decompositions as such a tool, and another thing called standard tree packing. But there's many other forms of this concept. Okay, so I'll repeat the slide later when we go to the shortest paths. So for now, forget about it, and I'll just try to give you a taste of what's going on in the Gomory and Hu all pairs max flow result. So the first step in what we do is actually this reduction that I mentioned from all pairs to single source. So I'll try to explain how that works. But even before, let's start with the Gomory and Hu algorithm itself, the classical one. So here's how Gomory and Hu computed the Gomory and Hu tree. So they have a graph, and they're trying to compute a tree. And in the beginning, everything is in one like super node, and they start refining it so that at the end they get the Gomory and Hu tree. And the way they do it is that they just pick an arbitrary pair, ST, and they find the minimum cut between them. And they use this minimum cut, big S, big T, to refine the supernode that they have. And so, they put, they refine it and they put an edge between these two supernodes, and the weight of the edge is exactly the weight of the minimum cut that they found. Okay, and now they continue recursively on each of these supernodes. So let's say they want to continue here on S, big S. So what they do is like they zoom in on S, and they pick a new pair within S, this S prime, T prime, the red ones. And they try to find the minimum cut between them, but importantly, they contract everything that's outside the supernode. So in this case, this big T, they contract and adjust the weights and all. So they contract, they compute the minimum cut, let's say it's this prime T prime. Good, so they use that to refine the tree. So S gets refined to S prime T prime. The weight is the weight of the cut, and then the T is connected in the right way. So there T ended up on the T prime side, so that's why it's connected here and not there. So you get this. That's how it works. And the reason it's correct is really this lemma, that is sometimes called the submodularity of cuts lemma, which says that it's okay to contract. So it says that when you contract the minimum cut, if you contract T and you look for the minimum cut in the contracted graph, it will be a minimum cut in the original graph. So it can't be that the minimum cut between S prime and T prime has to separate T. It doesn't have to. It can keep it all on one side. If it had to, then that would violate the minimum cut. You can prove this. It's not a difficult proof, but it's like extremely fundamental property of cuts. I mean, and the reason contracting is so important is, imagine you're refining some node, right? You want to contract everything else, because if you don't, and you look for find a minimum cut here, and that minimum cut somehow says that this thing has to be separated, I mean, you don't want to start separating these other things. So this contraction lets you keep a tree structure. Okay, so that's the original Gomory and Hu algorithm. What is the complexity here? So you can clearly see that the complexity is n-1 times max flow or big cut, because every time you run it, you discover an edge. It's n-1 edges. Okay, so that's the n times max flow. And now it's very natural to hope that maybe this is actually better, this subcubic, because when we're contracting, the graphs are getting smaller and smaller. So maybe the total time would be better. Right, so in particular, imagine you were cutting, every time you were splitting, it was going in half. You're getting a balanced cut. Right, so the first time it's like half an hour. So you get this like log levels of work, and at every level, you can imagine that in everything is contracted except for like one group. So the total work you're doing per level is actually linear. So that would end up with like logarithmic overhead times the maximum. So that would actually work if you were lucky enough that your cuts are balanced. The graph, it doesn't always happen. In fact, most of the time it actually does, like totally fails. For example, this very bad situation of a very deep tree is very common. So in this picture, you see that you start refining all the nodes, and then you see that one node got out, and then everything else stayed in the. So it's like you try to compute a cut from S to T for an arbitrary pair, and the cut that you got is T is on its own, and everybody else is on the other side. So you've learned like one thing. You reduce the size by one. And if this keeps happening, then that will be n. That's a bad situation. The depth might be omega. So then, okay, so this is a problem, and it can be a problem. You can try different ideas, like sample a random pair or something. It's not gonna help. There's like there are examples where it just doesn't happen. But then what we did discover is that if you did do, instead of sticking to single pair at that, like I think you're computing at every level is just one kind of cut. You can compute more cuts at the same time and then make progress. So there's different notions of more cuts. One elegant notion is single source cuts. So it's like you pick a pivot node, random node, and then you compute the minimum cut from that node to everybody. And somehow you kind of organize them in some kind of thing. And so if you got all these cuts, then you can learn like basically all the neighbors of that node in one shot. And you, moreover, for random node, you will be guaranteed that it will be a constant fraction in each one. So then, if you keep doing this, picking a random node, finding all the single source cuts from that node, then after log n levels, it will be fine. But of course, this problem, this single source problem, is a much harder problem. It's no longer like just making a single query to max low. It's just it's a problem that you have to solve, and that was the point of what I was trying to say. That we got a reduction from all pairs to single source. So the reduction is basically this sample random node. So that all I've discussed so far, I would say, is part of this like combinatorial algorithms. Wow. Good. So the next thing I want to do is discuss this data dependent stuff, the structural analysis, and try to give you a taste of why that helps for our problem. So this goes into when you try to solve the single source problem. So now imagine you have a pivot, this node P, and you are trying to find the minimum cut to everybody in the graph. And you're trying to beat the naive algorithm that for every target it computes the minimum cut with a query. And so what we at a high level, what we do is we say, okay, let's compute an expander decomposition of the graph. I don't want to go into the details of the expander decomposition. Roughly, it's decomposes your graph into some number of expanders, these well-connected graphs, with some parameter of expansion, and some sparse outer edges. So the remainder is like sparser. How sparse depends on the parameter composition. Yeah, so you take your graph, you do this, and now you apply some wishful thinking. You say, expanders are really something I don't want to cut. If I have a minimum cut between P and some other node V, it doesn't make sense to cut an expander. Cutting an expander is like kind of relatively dense compared to the outer parts. It's it had to be kind of yeah. So therefore, like wishful thinking is that all cuts are going to look like this. They're just going to avoid expand. And if that's true, well, then it's easy. Then I can pay only one query for each expander. Like the same cut that I got for V is going to be the cut for everybody in that expander. Like everything in the expander is like kind of one. I mean, treated together. And then I save on the number of queries. I need to only do like based on the number of expanders, not on the number of nodes. So this is, of course, at a high level, there's all the parameters that I'm hiding, but like this is an idea that is at the heart of what's going on. One complication that arises is that, of course, you can cut expanders. You can cut them a little bit. Sure, you're not going to go in the middle of an expander and cut. That's going to be terrible. But taking some small number of nodes, it actually might happen. Expanders are not like perfectly clean. There's always these error terms. And yeah, so this is a complication that we have to deal with, and I just want to highlight this thing called isolated cuts, which is like that tool that helps us do all these cleanups and deal with these things. It's basically a way to compute a lot of small cuts at the same time. It's like you run one of log n calls to minimum cut, and you simultaneously get a lot of minimum cuts as long as they're all like kind of logarithmic. That helps you do this cleanup. And this tool has been, probably heard it like other ways. It's been used in like tens of papers by now on all sorts of cut stuff. But I'm not gonna discuss it further. Okay. But this is what I would say is more is again like an algorithmic type of thing. So if I want to put everything into the one picture of technical overview picture, so we started with the goal of computing Gomory and Hu trees, and at the end of the day, we reduced it to computing max flows, polylog overhead of max flows, and this is like our powerful tool. And along the lines, there were like two algorithmics going on, like this reduction to single source, and then this isolating cut state, which reduces to off log and max flows by some dividing factor. It's like a simple thing. And then in the middle, we had this, structure analysis where we applied expanded decomposition. I mean, I explained why expanded decompositions come in. There's another thing we use, which is the standard tree packets. It's a different way to analyze graphs, which is for weighted graphs to get linear time, it's still needed. For unweighted graphs, this would have been enough, but yeah. But I'm not gonna go into it. Good. So that's basically the end of my overview of pairwise flow, and I want to tell you what I've been excited ever since. What I've been excited about is to try to push on shortest path. And so the takeaway is basically this slide with the three kind of ingredients. And now, I want to start like discussing what it might look like in shortest path. So that's like our motivating question now, can we learn from this for shortest path? And so let me say what would happen if you did break shortest path, like how bad would it be? So you would break one of the three main conjectures of the field. What does that mean? So shortest path has even stronger versions of it. So these are like other conjectures, less kind of famous, but still each one of them has its own like substantial class. And these conjectures are basically saying that APSP is still hard, even if the graphs are coming from a certain other problem, they have certain product structure. In particular, this conjecture said that this graph is hard even when graphs have a product structure. This one said that it's hard even when they have like when you use convolution to matrices. It's some other structure that even though it's a new structure, the problem is still hard. So anyway, what would happen? So if you break this one, you break these other ones too. Some of these, like the APSP conjecture, it has an equivalence class. So a lot of the problems in the class are equivalent. So you would also solve them faster. You would get a new algorithm for a lot of graph problems. I guess that's not surprising. APSP it captures a lot of other shortest path related problems. But then there are all these problems that are not equivalent. They're just hard under that problem. And there's lots of them too. And these problems will just not have lower bounds, and then you can work on them too. So it would be a mess, but this can happen. And I want to highlight that when we think of fine-grained complexity, I like to think of it as just we are pointing at the problems to work on. So there were hundreds of problems. You could have worked on all of them. Fine-grained complexity is telling you don't work on all of them. Work on these kind of conjectures that we're highlighting. There's like three main ones. There's 10 other ones. These are the problems that everybody who's doing algorithms should kind of be working on, because we have to solve them. Like these are really the edge of what we know. They are like the easiest problems we can solve. So I just want to highlight this perspective. Like these conjectures are not meant to be like laws of nature. They're meant to be like guiding algorithms research to what to work on. Good. So APSP. So how would we solve APSP? Let's use this recipe. And let me suggest some ingredients for these recipes. Of course, maybe people can come up with totally new things, and that would really be great. But here's some suggestions. So for the combinatorial algorithmics, I claim that we have a very nice tool set already because of these reductions to triangle or matrix problems. So let me explain what that means. So I already mentioned, to solve unweighted APSP, you can use matrix multiplication. So there's some kind of equivalence actually to Boolean matrix multiplication. So it's not just standard, but even like more of a simpler thing where it's like OR of add, which actually this you can think of this as a APSP on 3-layered graphs. So this is basically saying you don't have to worry about like arbitrary complicated graphs. The problem is equally hard if your graph is just 3 layers. And when you have 3 layers and it's unweighted, and let's say you just want to figure out if distance is 2 or not 2, that's exactly Boolean matrix multiplication. For every node, for every like I and j, you're asking, is there a k such that they're both 1? Okay, so this is that's in the unweighted case, and we can solve it into the omega or subcubic, but we want the weighted. So in the weighted, the same thing happens. So you can still get this equivalence to the 3-layer case. And it's still a matrix multiplication problem, but like instead of like a Boolean, it's min plus. So instead of the sum, it's a min. Instead of the times, it's a plus. So it's a different operation, but it's still a matrix multiplication problem. And this combinatoric stuff translated this complex problem to just this basic just 3 layers, basically. That's what I'm trying to say. Okay, so now your task is now to solve this problem. And there have been a lot of attempts, and I want to highlight 2 directions to solving it. Right, so how do you solve this weighted, this min plus matrix multiplication in subcubic time? So of course, I mean, the first thing, which is not even here, like trying to use. Okay, so how do we solve the Boolean thing in subcubic time? Well, there's this Strassen and all these matrix multiplication algorithms. They divide and then they do cancellations and all that. That completely fails for min plus. The min, if you go from plus to min, you lose the power to do cancellations. It's well known. So just using like these Strassen-like ideas for min plus seems impossible. Okay, so then we have 2 other ways. One way is to say, let's reduce min plus to plus times. So not like apply it's like use it as a black box. Okay, we have this black box, this like Boolean or integer matrix multiplication. Let's reduce the weights. Let's remove the weights. Let's remove the min plus nature of it to get the plus times. And that's one direction. And then here you can even assume omega is 2. It doesn't matter. You're just trying to break the thing. And the other direction is trying to say, well, let's try to solve the unweighted thing, but in a new way, not with Strassen-like techniques, not with these techniques that don't generalize. Let's just try to find a totally different algorithm, sometimes called combinatorial. And then once we have it, let's hope that that one would generalize. So we're trying to come up with something new in the hope that it would generalize better. Right, so this direction is saying, let's just look at unweighted for now. We were trying to solve the weighted, but let's forget that. Let's solve the unweighted, but in a different way. This new way maybe you would generalize. So I'm going to discuss the kind of progress and ideas on both of these things. But I want to mention, like, I think both these directions are super promising and should be studied heavily. And in particular, like this framework that I'm suggesting is gonna make sense for both, because like a kind of basic test to think about is, do we know that what do we know about the random case? Like, if the random case is easy, then this structure, worst case to randomness, the structure kind of thing makes a lot of sense. And I want to say that yes, the random case is easy for both directions, in the sense that if the graph was unweighted and random, you can solve the problem so easily in like combinatorial ways that so you would be able to solve it here basically. And also here, if you had weights and they were random weights, then you can basically solve the problem again. Okay, so let's try to do this. And I want to start with this direction, talk about it, and then I'll go to the other direction. So again, this direction is, let's solve unweighted BMM in subcubic time. And so here there were some Good. So we're trying to beat NQ. And so the first improvement is this for Russians very old algorithm that is a log squared. There were some papers, one by Watching, shaping more by some other combinatorial like divide and conquer. And there was this paper by Bansal and Williams shaping some point something factor. But the method he was using is interesting, this regularity decompositions. And recently we've been able to use the same method, but like different regularity notions to get a super polylog shaping. So this is result is saying we can solve this unweighted thing with the new method at this time. So let me show a slide about this. Right, and so and this highlights like one kind of possible tools for doing
So then generalize this to mean class product.
yeah. So as I was gonna say, like now the hope is to two hopes. One is to go all the way to truly subcubic and to the 2.9. The other hope is to make these things work for weighted. So we still don't know that these things do work for weighted. We do think they should work, or some versions of them should work. Like they don't immediately work, but hopefully something like that will work. I think it's a great question to study. I mean, they're not like Strassen where it's like hopeless. But I'm talking about the regularity. The other ones, actually, these things do work for weighted. They have been, ideas from them have been used for weighted. Good, but yeah, so here that's what I'm suggesting. That regularity lemmas could be this tool that we're missing that we could use. And let me just quickly say how that might work. So regularity lemma tells you can take any graph and decompose it to these like regular random like graphs. And then once you have random graph, well, you just if it's dense and random like, then there's so many paths basically. The answers would be yes on those structures, and then everything else is sparse. You can solve it faster. And so, like the only question is, what is this regularity notion? How many, what are the parameters? Like, how many pieces that the regularity give you? And there were different notions like Semeredy, Friis-Canaan. Each one gave a different count. And we've used the new notion like grid regularity that was very similar to the one used by Kelly and Mecca in their breakthrough for arithmetic progression resets, where they also have this kind of bound. But yeah, so we viewed that notion and we got this. The paper was about proving a decomposition theorem using this notion, and we get this bound. Okay, so that's that was this part with the combinatorial. Now, okay, let's go back to the weighted. And here now, what I'm saying is we have this powerful tool. Let's use it as mesh multiplication. And I'll just quickly mention that the current best algorithm for APSP can be viewed as doing this. So this algorithm by Ryan Williams, it uses some polynomial method, circuit complexity, to translate min plus 2 plus times in some fancy reduction. But that's not what I'm going to talk about. I'm going to try to say something else here. And like the first question I want to answer, which somehow surprisingly maybe we don't understand, is well, what are the hard instances? What are the hard instances of APSP? Okay. So what do the weights look like to make the problem hard? So what do we know? So first there's this old algorithm where if the maximum weight is m, then the running time is m times n to the omega. So what this says is that if m is less than n, sublinear, then you're fine. If omega is 2. So then the weight had to be at least n and above. And in principle they could be anything, like n squared, n cubed, n to the 10. But there's this strong APSP conjecture that people have looked at and used as a basis for lower bounds to show that says that yeah, n is actually just as hard. So below n it's easy. And this conjecture is saying if it was more than n, you can bring it down to n. In other words, there are hard instances where the weights are from 1 to n. It's a conjecture, and we didn't know like even simpler things. For example, if the weights are big, but there's few of them. Let's say there's only root n distinct weights. So all these n squared edges, there's only root n different ones. Not even n different things, just root n. Is that easy or hard? And so this is something we've solved recently with the ex-postdoc Nick Fisher and the group from MIT. So we answered this question. So we showed that, yeah, if you have a sublinear number of distinct weights, the problem becomes subcubic. And then later, Nick Fisher, he built on this to actually prove the strong APSP conjecture. So this is a breakthrough paper I'm like super happy with. It says that so this like conjecture that people were introducing and using, the strong one, it's the same as the APSP conjecture. So it unifies two conjectures, but it also explains to us that what are the hard instances. The hard instances are, yes, the weights are 1 to 1. I mean, there's more to understand about them, but at least the very first thing you might ask, now we know. You can focus on the weights in 1 to n. And both of these results, they use the additive combinatorics, and let me just finish with that. So I'll highlight one like structural analysis tool from additive combinatorics that you might use in this context. So this is the Vallov-Szegedi-Szemeredy-Gowers theorem, the BSG theorem. So the starting point, like for why additive combinatorics even comes in, is that you can observe that this algorithm, the m times n to the omega algorithm, you can generalize it to this algorithm. So if the set of weights is big S, then the running time can just be the sum set of it. So S plus S, the size of the sum set times n to the omega. So if your weights happen to have a small sum set, then you're in good shape. And then that's how the BSG theorem comes in. So it's a theorem that says you can take a set of numbers or weights, and you can decompose them into small number of subsets, and each subset has small subsets. So basically, you take your graph, you look at the weight, you apply BSG, and then you apply this algorithm. There's a lot of details, of course, rushing over, but that's what's going on. So that's the end of the talk. Just to summarize, we had this kind of counterintuitive separation, led us to wonder maybe APSP should be solved. I kind of presented this 3-ingredient type of thing and tried to say for APSP what it might look like. And of course, we really want you to think about this and come up with more suggestions. Thank you.
Any questions?
So, in areas like this for matrix multiplication or for general for this the sum?
It's gonna be it's for both. It works for both. I mean, it is specifically first you solve it for the matrix multiplication, but the 3-layer
You can redo it.
You can redo it. Yeah.
And the more general question. So one difference seems to be that for the flow there is a small data structure. If someone gave you that data structure will be done, is there something like this for APSP? Anything of size less than n squared that would get me anywhere further and that I wouldn't need to work on crash?
Not really, no. No, there isn't such a thing. What there is a non-deterministic algorithm. So there is a non-trivial non-deterministic algorithm that's n to the 2.5 roughly. It's omega is 2, which but it's not what it's guessing. What that algorithm is like guessing is some kind of way to reduce the weights. Basically, it's guessing let's say some prime value from 1 to root n, such that you take the weights modulo that value, the number of false positives is small. So it's not like a graph, really a graph thing. It's some kind of, it's within that direction of reducing the weights. There is some observation that says, yeah, if you had some information, you would. But it's, yeah, like a graph thing that makes it easier. Yeah, I mean,
So there's a big difference combinatorial.
it's a big, yes. So, right. So I maybe I forgot to say it. So we had all the evidence that shortest path is easier, but there was one evidence that Maxwell was easier, which is the Gomory and Hu theorem itself. That there's this structure that encodes all the information in like just of n minus one edges. And it's exact. It even says that the number of answers is n minus one. Like this n squared answer is n minus one different answers. For shortest paths, all these things are full. Like the number of answers could be n squared. There's no compression that you can do that's exact and so on. So like information theoretically, that was like evidence in the other direction. So what we've done basically is just show that it's algorithmically as well. But yeah.
You have a linear time piece over, how does it change your calculus?
No, it's something I always assume. In the sense that, like, in the sense that if I manage to show that using an LP solver, I solve APSP, I would be saying, oh, look, there's a lower bound for LPs.
Right, so can you use an LP solver for over Maxwell?
Not directly.
No.
I don't think. Yeah. I mean, now you can do, but.
Actually, I want to ask which might be mad that can you use the machinery under max flows to do something about APSP?
Oh. I don't know. Maybe. Yeah, maybe.
Or do you have any intuition where this is?
I mean, I was gonna say, look at LPs and try to come up with an LP for shortest paths, and that seems very hard, but that doesn't even know. Maybe we can use the machinery, like these dynamic data structures and all of that, like somehow inside like multiplicative weight updates. You don't have to have an LP to apply the machinery. Yeah, why not? I don't know. I actually haven't thought about this.
Okay, if there aren't any questions, let's take a minute.